Mhm.
All right, and you may begin.
All right, hello. Welcome to Portland State University's Friday Transportation Seminar. I'm Kelly Clifton, a professor in civil and environmental engineering. For those of you watching online, welcome. I just want to remind everyone that you can ask a question at any time using the GoToWebinar questions pane. And then this evening we will post the archived version at the TREC website, trec.pdx.edu. And just one reminder before we start today's seminar that next week we will have Dr. Alex Bagazzi, an alum of PSU. He's now an assistant professor at the University of British Columbia, and he's going to be presenting That Bike is Too Heavy, Merging Bicycling Physics, Human Physiology, and Travel Behavior. For those of you here and online that wish to attend, we're going to be in a different room. Next week we will be in the Carl Miller Center, room 605. And so today it is my pleasure to welcome Dr. Haizong Wang. He is an associate professor from our neighbor down the street, Oregon State University. And he's going to be talking to us today about a thing that's on everyone's mind, disasters. So earthquakes, tsunamis, volcanoes, and how transportation planning can help make us more safe. So, thank you.
Thank you, Kelly. I'd like to start by thanking everyone for your time and for having me today. Again, my name is Haizong Wang, Oregon State and School of Civil and Construction Engineering. And before I start, I would like to acknowledge some of the contributions. It's not one-person work, it's a big team with my collaboration with one of my PhD students, Ali Reza, and my colleague, Dr. Dan Cox, in coastal engineering and civil engineering at OSU, and Laurie Kramer from School of Public Policy. And this is the perfect timing for coming to PSU again. Actually, just 3 weeks ago, less than 3 weeks ago, I was on campus with the EERI event, and with we have one of the panelists over there in the audience as well. Make sure this is working. Okay. Okay, so let me make sure that this is not working. Oh, it's working. Okay, it's working now. Okay, this is the research team, and we have postdoc, PhD, and undergraduate students. And so today, the topic that I would like to share is about earthquake and tsunami associated with the Cascadia Subduction earthquake. I actually just came back from a trip to Palu, Indonesia, a few days ago, and spent a week over there. And the trip was about the first project that's supported by NSF. It's a rapid project, collecting data, local residents' response to 2018, the Palu earthquake and tsunami. We spent a week over there and collect about 503 households, their response behavior in the earthquake and the tsunami. And the purpose, that's done actually by interviewing the people in the household. Many of them actually are still in the camps because their homes are just washed away. And I will share a few pictures over here. And this is the pictures that I outlined regarding the deadly earthquake and the tsunami in Palu that happened September 28th of last year. And we have done this survey, about half a year later, but the community is, still, having a long way to go ahead to recover from that disaster. So for this project, we have that's my collaborator, Dr. Michael Lindell, and Dr. Ahmad Hussein from a local university. And many of you who have, paid some attention to this event, that you might have seen the pictures on the right, which is actually, a mosque of people who go there, pray regularly. And now, currently, that's already in the water. And basically, that tsunami and earthquake that have changed the coastal landscape, and about more than 100, some areas of 200 meters, which is more than 600 feet, are right now underwater. So the coastal, the entire the coastal community in the city of Palu has been affected, and also Donggala, which is 2 hours away, which is where the epicenter is for that earthquake last year. So we had hired through a local contact, working with a local university, hired 50 students to help us to interview. It's not done by a mail-in survey. It's a personal interview. we had so many stories to hear from them, and many of them still are recovering. And we had one one household we interviewed from the students, and it was a brother and sister, and they lost their parents, they lost their grandparents, and they were stationed in the camp. So it's really tough to interview and hear them story again. But this is very important to knowing their behavior. What are some of the actions that they take, and were they warned? Did they recognize the earthquake ground shaking as a cue for potential tsunami arrival? So those are many of the questions, and this is one of the in the corner over there is a picture that about one of the camps within a city. We visited a few camps over there, and so this data set, we are really hoping to learn from this relatively recent disaster, which actually share a lot of similarities to our coast and our Oregon coast, and also the West Coast, which suffers from Northern California to British Columbia, and even portion of Alaska, suffers the earthquake and the tsunami event. So I'll play a short video. This is actually a video from the 2011 Tohoku event, which is 8 years ago, and this this is not a simulation, it's a video clip at an intersection, basically showing that oncoming hazard of tsunami with the debris, and also the people who are using it, not necessarily they are knowing that oncoming hazard. And so in this, this big event actually taught us and taught basically the Pacific, many of the coastal community on the Pacific, around the Pacific Ocean, that how deadly that earthquake could be, and especially with the magnitude 9 that we're expecting. And associated with this earthquake, the event in Tohoku in 2011, the computer scientists that worked at the University of Tokyo, they have unintentionally collected data from the people who are using cell phones, who are using GPS. And this is a video, this is a visualization from the computer scientists. And this video is very neat because it includes before the earthquake happens, and the point that the earthquake happens, and also the post, a short time period after post disaster. So we'll see this over here is a flowing, the traffic are flowing, and this is and only the data that the people who use the cell phone and GPS. We'll see that spot pretty soon. That spot, on the March of 11, this is the time that when the earthquake happened, and it actually, you can just feel basically that put the city in a halt, and you will see that the pattern that the people are spreading. And this is not the area that affected by tsunami per se, but that earthquake ground shaking was pretty it's pretty significant. And also interestingly, during my trip to Palu, Indonesia, over the data collection trip, there was a 6.8 earthquake happened, after 3 days that we arrived over there. I was already sleeping in a hotel after a day of, traveling in that area, and suddenly, it was a very strong ground shaking. And I didn't realize that was an earthquake. I feel am I dreaming, or is it something happening later on that the collaborator already run to the hotel lobby, and she called me and asked me if it's okay. And then I realized, oh, this is an earthquake. And the ground shaking was pretty significant, but the epicenter was a little far from the city. So there was tsunami warning, but the tsunami warning was lifted later on. And there wasn't much damage to the hotel that we stayed, but the ground shaking was pretty significant. That's actually my first earthquake experience, and also during a trip that collecting data for earthquake and tsunami, which is quite unique. And so today, what I would like to focus on is not necessarily a specific research question. It's about associated with the Cascadia Subduction earthquake, and how are we using some of the modeling tools to help the communities and help our communities to be ready for that, and what can we do? And the disaster research in transportation often involves, it's a multidisciplinary area, often involves transportation engineering, transportation, urban planners as well, but has to working with this, the social community, social science and psychological, and many expertise are required. So, this is a definite adapted from earlier Dr. Dennis Miladi's definition about disaster, which is the overlapping area that in the middle over here, the natural system, which is the hazard, and the built environment, and the social economic system, and the overlapping area is where the disaster science is actually defined. And that we use this figure to illustrate that this is basically the area that the multiple systems are integrated, and with an increasing level of integration. And speaking of the Cascadia subduction zone, this is, we often put it as a rapid onset disaster. And there are slow onset disaster and rapid onset disaster based on the warning time that we have. And the figure that you see from here is on the horizontal axis is time, on the vertical axis is distance. And what we see from here, the earthquake, and basically, no time to evacuate. The best is we can just, run out of the building and to the open area. And I had a reconnaissance trip to Mexico City earthquake in 2017, and following the 2 earthquakes in Mexico. And in Mexico City, there are, within the city, there are just the spots that defined, for different community, different, building, where are the gathering areas, and putting signs over there, okay, telling people that this is the area that it should be evacuating to. And on the other side, is our hurricanes, which are, not, it's familiar, that happened almost every year in this country. Those could be the leading time could be many hours to multiple days, and based on the current forecasting and prediction. The near field tsunami that we're talking about today, that on our coast community that hazard that exposed to, is not very long of a leading time, but not that short either. It's in a magnitude of 20 to 40 minutes, depending on where you are on the coast. So it's, it's really is, you have time to evacuate, but you don't have that much time to prepare either. So it's in that's what we'll be talking about. And the different from a near field tsunami, there is a far field tsunami as well, which gives about warning time in the range of 4 to 6 hours. And that's in roughly close to some of the wildfire events. There are wildfire events give shorter lead time as well. So there's a lot of information. I'll make. We can check back this figure over here. And where today, in my talk, I'm using a real community, which is the city of Seaside. How many of you have been to city of Seaside before? Well, many of you. That's great. And I've been to city of Seaside for quite a few times, for collecting data, just working with the city engineers and interview some of the hotels and trying to get a projection of where the tourists, how many of the tourists, and where they are distributed. And what we use is an agent-based modeling framework to couple 3 things that, like what we see in the video, which is the 3 systems, which is the social system, which is the people who are using the system, and the infrastructure, which is transportation network, and also the hazard, which is following the earthquake, there's a tsunami, and so we're coupling that 3 systems together and trying to use it as a scenario evaluation tool, and to help planners, help engineers, and to prepare for the event. And some of the things that we can do, is using for evaluating evacuation plans, for people who are making diverse set of decisions, and what are the likely, the life safety outcomes associated with the decisions that they make. So for those of you who are not familiar with an agent-based modeling framework, it's also used as ABM, which is a little different from the activity-based modeling in certain ways, but they share a lot of similarity as well, because they're all going to a finer level of details. And the agent-based model that I'm using, we developed it, over the past few years, is used through a NetLogo, which is it's an agent-based modeling platform, but you have to do a lot of coding associated with it. So this model actually integrates a couple of data layers, and we have, on the left-hand side is the population distribution. Primarily, we consider 2 types of population, residents over there, and also the people who are traveling over there. And I looked at a report from Travel Oregon that, Oregon coast every year attract about 17 million people on a yearly basis. That's actually a huge part of the coastal economy. And the other layer is the evacuation shelters, and these the yellow circle area are those city decks and tsunami evacuation shelters. Some of them are schools, some of them are hospitals, some are high grounds. We have visited each and every one during our trip. And the other data layer is the tsunami inundation. That's actually computed from a model that developed by NOAA in the past more than, I would say, probably 40 years. And it has been pretty mature. It's caught most. And that is computed separately and fed into the model as basically the interaction of the hazard with the built environment. And again, on some of the sort of material on what an agent is. And in the agent-based model, each person is modeled as an agent. As an agent, the person has the ability to see and to think, the reasoning process, and also you can make decisions. What's the next step? What's your movement? And I give credit to the professor Huli, at Tokyo University, and the material some of them are from his publications. And the agent-based model, the powerful piece is the agent-based model is a bottom-up approach. Basically from defining simple, it doesn't have to be complicated. From simple rules that we can look at the system as a whole and to look at the emergent behavior that at a system level that we're not necessarily expecting those behavior, but at the simulation can tell us what are some of the potentials and what are the likely happening scenarios. And for the, each of the agent has dynamics, basically is the movement, and the X over there is the position. We know that, differentiation of that is speed, and that speed is depending on, how many people are around you, which is like a crowd density. If you're walking freely, just like driving a car on I-5, if you are the only one, you can drive at a free flow speed. But in a room, there are crowded people, your speed will be penalized by how many people are surrounding you. And so that, basically your view from the environment, which is E over here, and also the characteristics of the agent, basically your age, your gender, and those are, gender in the social literature that is, is not necessarily directly influence your walking speed, but the age is playing, certainly playing a role over there. So basically, if we look at the agent, modeling that agent over here as, IJ agent, this agent potentially can move into, forward directly and different directions or backward. And there are probabilities that, that agent can move to. So basically that's, each person or a vehicle can be an agent. Since there are agent communications, there are also agent communication and agent movements. In the movements, we're using a so-called a social force model. Some of you are probably familiar with this one. This is proposed by Dirk Helbing in 2000, published on Nature, and basically is looking at, on the left-hand side is Newton's second law, and on the right-hand side is a few terms that one's a self-driven force from the agent, and the other one is the people and the people interaction, and the third component is the people's interaction with the barriers. For example, in this building, if something is happening, we need to leave the building. If we're leaving it simultaneously, that's the exit. It's not here, not there. That's the locations. So people will be forming at the door. It's the arching behavior that has been produced from this one. So we're integrating a modified version of the social force model into the agent-based model over here. So let's take a look at the model that we developed using City of Seaside as a case study. And basically, this is the four different data layers, and with the population distribution that you see from there, and with the transportation network. In this basic version, basically we haven't incorporated the earthquake damage to the infrastructure yet. And there's a river that in City of Seaside bisecting the city with multiple bridges that, these are multiple bridges on the river, and this is US 101 passing the city as well. And these are when the simulation starts is when the earthquake happened. So, and we are using that, integrating different social behavior. For example, how long that, for that individual or household, how long it take to be ready to leave, and also, what route did they take, and are they using, the shortest path or other, the routing behavior is also part of the evacuation process. So what we see over here is after after earthquake, the tsunami is already generating, but it takes time to propagate it to the city. And what we see of the color change over here is actually the tsunami wave height. The darker the color, actually the higher that the tsunami wave run-up height. And use this model, we are able to look at where are some of the bottlenecks that are happening in the city, in the network, and what are some of the vulnerable locations. And so what you see is each of these agents representing a person or a vehicle, could be a vehicle. And when they are turning red, which means that they have interaction with the wave, just like what we see from the video. And in this, in this simulation, we're actually not taking in consideration people's swimming skill. And your swimming skill, if you're an Olympic swimmer or do not swim at all, is not making a difference, because the water that we see over there earlier is actually not swimming water anyways. So this is a model, a framework that we built in the past few years, and still trying hard to validate it, because it's a simulation. How should I trust that simulation results? So we take many different ways trying to validate. One of the things we try to validate is walking speeds. And based on the AASHTO Green Book, we know that people normally can walk about 4 feet per second on average. That's normal situation. But in a disaster situation, people tend to walk faster. So we use a normal distribution to try to just basically incorporate the walking ability from a diverse population. Some people walk faster, some much slower. So that's one of the areas. The other one is a meeting time, basically how long it takes an individual or household to be ready for to leave. And this is using a Rayleigh distribution. On average, okay, people take 5 minutes, but depending on that variation over here, you see from the different variation in the parameters that that meeting time can go up to 10 minutes. So this is another variable which is critical. And our in the previous the video that I showed over there, one of the messages we keep communicating with people is minutes matters. And minutes matters, and don't waste the time, and leave right away. And there was a study from Japan following the 2011 earthquake, and they were starting for a community. If people actually can leave within 17 minutes, and they are very likely to make the life safety to the shelters and to the high grounds. If they are leaving actually 1 or 2 minutes later, and their probability of surviving is much lower. So it's really that minutes matter message is a key message that we wanted to stress all the time for these rapid onset disasters. And so the other I mentioned about the agent-based model using simple rules, and to elaborate on that just a little bit. And this is again the city of Seaside transportation, the model, the transportation network. And these are the city designated tsunami evacuation shelters, and they are there. And these are the spots that, there's a few people that Yu-Mei Wang and Jay Raskin and many people are working at the community, and there are also discussions at the community. What are some of the potential vertical evacuation shelters if they put that? What are some of the candidate locations? And this was specified in a paper that they published on the ASC Natural Hazards Review called 50-Year Resiliency Plan, something like that, for City of Seaside a few years ago. And these were some of the locations that discussed in the paper. And we took that. And the agents evacuate options, we call it 0, 1, 2, 3. Basically, 0 is just sheltering in place. I'm not leaving. And that actually, in a 2011 event, there was a small percentage people that didn't leave. And because there is an earthquake happening so frequently in Japan, and often there follows tsunami warning, but people are not leaving. The people left, but the tsunami didn't come. And that happened, repeatedly, 10 times. And then later on, people just are, like that, the crying wolf scenario. It's just not living anymore. And this one is the real big tsunami came. And so one of the 0 is sheltering in place, not leaving. And 1 is just evacuation horizontally, walking on foot. And 2 is evacuation horizontally, but could be using car. But in our model, we only consider 2 modes: it's walking on foot and evacuation by car. And the third one is vertically, just finding a higher building or high ground, and to that when you are running out of time, that when a wave that you see that wave is coming. So those are the 4 options in the model. And we, like I said, it's a simulation, but how can we increase the credibility of those simulation results, and we can communicate with the community and use this as a tool to evaluate the different, type of, strategies and behaviors. And working with the Oregon Department of Parks and Recreations, in 2017 to in 2018, we have conducted 7 drills at a South Beach State Park. And those are, some of the drills. This is showing the dates of some of the drills. And we the first one, we just try, we just want to test it and see how it goes. And so we have a smaller team and students, researchers, and also we have a few people, from the Hatfield Marine Science Center, which is very close. And each of the drills are increasing complexity. And for example, this one is simulating people are, with disabilities and with, attached marble on the shoe. To simulate the people's, walking speed is penalized by the, their disability or could be potentially age as well. And some other scenarios, with an envelope that, okay, you are supposed to be reunion with your family, or you are supposed to go somewhere to pick up your kid. Just trying to simulate that, those different scenarios with each of the evacuation drills is a little different and complicated with increasing complexity. And during that evacuation drill, and there was a pre-evacuation drill survey and asking people their experience, and also there is a post-evacuation drill, like a survey, not like a structured survey, but asking their qualitative assessments, and trying to get inputs, how their experience was, how does that change their risk perception, the personalization. And during the drill, we actually used an app. We initially, in the project, we proposed to develop an app, but later on we actually used an existing app. Many of you probably use Strava, which is a cycling app. You can actually change to a walking mode as well. And so each of the participants is equipped, they all have smartphones, and with the app and all their, with the starting point, which route that they took and their walking speeds on the different trails in the South Beach State Park, all those data are recorded. And basically, that provide us, it's not a real scenario, real evacuation, but it also provide us, some of the data that can help ground truths of the simulation model. And this is a short video that we tried, we created using the South Beach State Park model as, as a validation scenario. And what you see from here is the red dots are real people, are the people who participated in our evacuation drill. I'm one of the dots. I was one of the dots. And the other one, the triangular one, is the computer-generated agents. So, and with that, so we station basically, okay, there's a few real people here. We station a few computer-generated agents starting the same location. Let's try to see and what are the differences. And the other one is interesting to see is a few participants, is these dots from the Hatfield Marine Science Center. They practice drills regularly. And so what we found is, and for many of these, some of the dots over here are first-time students visiting the park. They just lost their way. They are not able to find, they are supposed to be going to the safety havens over here, but they're just not going toward the hazard because they lost their way in the first time. But for people over here who have practiced the drill multiple times, they know exactly where it is. They know the route. So their behavior is quite consistent with the computer-generated agents. But for people who haven't done this before, the first timer, and it's very likely they lost and they do not necessarily know. And then we have to drive back to to pick them up and to rescue them. So this is this is just like you see earlier. That's the city of Seaside, but this is the South Beach State Park model, and this is the bay. Many of I used to go here for crabbing. So this is a scenario that actually quite close to the Palu earthquake and tsunami. They also have a long bay over there, which is actually we can see from the simulation is the wave are traveling actually much faster in the bay, in the channel. And also there is a jetty, the road over here. It's flat and you can walk faster. But actually walking on the jetty, you are not gaining elevation. But walking actually in the park, and the road is not as friendly to walk, but it's actually you're gaining elevations over the course of the walking. So what you see from here is this cross dots are the places that are real agents, are real people that are who lost and also caught by the tsunami wave. So we're just trying to understand and work with the Oregon parks, and they are trying to help. They are trying to evaluate, are they providing enough tsunami evacuation signage and number of signage and where those signage should be placed in the park, so that can provide guidance to the people that who are doing camping over there. And we also tried actually to recruit real campers over there in the community through the parks. And we did get one registration, but later on he or she did not attend that because it's quite an effort of time to participate. And in one of the many evacuation drills, this is one of the tsunami evacuation drill we call Tsunami in the Dark. And it's happening after 9 p.m. After 9 p.m., we group that, these are students are actually REU students. They live on campus at the the Hatfield Marine Science Center. The tsunami in the dark, simulating the hazards that are happening in the night, and the people with not the best nighttime visibility, and simulating the marble stuff, and simulating people with disability. And so this was the group, and we provided this ice cream after the event. Everybody was still smiling after. It is already midnight by that time. So using these type of drills, we actually are collecting a valuable data set. You may argue that okay, it's not real events, but those are not something. The real events is rare, and we hope it's not happening, but it will. It will happen. It's not about if it will happen or not, but when it will happen. And the other neat data set that collected from is the Seaside Tsunami Evacuation Expectation Survey. This was sending out more than 1,000 envelopes with the survey. And generally, for this type of service, my colleague, one of the co-PI, Dr. Laurie Kramer, was leading about this effort. We get about more than 20% of response. So you can see the data here is about 211 total samples that we received, and this is the number of the population based on the census data in city of Seaside. And what you see from here is that how that sample, these 211 sample are distributed, their household, based on their zip code and approximately where they are located in the city. And we're also trying to use this is what we call a tsunami evacuation expectation survey, including like more than 40 questions and associated with their risk perception and evacuation logistics and their disaster experience, and many questions. It's I just picked the 2 questions from the survey. It's a long question, not have enough time to present that. In one of the questions, which is question 8, do you agree or disagree people could increase their chance of surviving by preparing, make your evacuation plan, emergency plans, proper actions. And we can see the response, it's about agree and disagree combined together is about close to 83%. So people has that believing that preparation could make a difference. And the other one is about the assessment of the general level of community preparedness for the Cascadia. And we can see and the percentage of the people combined together, 46% people believe that we're lacking of preparation and the preparation is poor. So there's a lot of rooms to improve that in that piece. So we have talked so much about the model, and you may have the question, okay, why do we care about this model? What this model can help? One of the application could be this tsunami evacuation or evacuation in general are likely to be multimodal, and there are people who will be choosing to walk on foot. There will be people who just don't want to leave their Mercedes-Benz behind, or just inundated by water. There are different reasonings. So one of the questions we try to understand better is 100% pedestrian walking on foot better, or certainly probably just everybody is driving. Probably we know that probably is the least favorite. So this one has a lot of curves over here, but what you see actually each one is an agent moving, and these are actually the trajectory that we extract from that the Strava app, collecting from the real people. And the other one is that we didn't do car evacuation in the park, so we skipped that. So some of the car trajectory is actually just a simulation. It's not from a real participant. And one thing that we found out is this. I'm not trying to emphasize this is the optimum split between the pedestrian and people who are driving, but the hypothesis is there is a split that likely to having a better life safety outcome than the others. So this is on the horizontal axis is the percentage of the people who are percentage of people who are choosing walking on foot, and with the mortality rate. And what we see is over here is the higher percentage of the people who are, let's see from here, the pedestrian mortality rate, and also using vehicle evacuation. And this solid curve is the total. So what we see from here is, but this is also affected by many other choice of parameters. When did you leave, and also your walking speed, not just the modes, the modes that you choose. So we try to identify if there is a optimum split over there, and this is also informed by the 2009 American Samoa earthquake and the tsunami. And there are actually many people used cars in the evacuation. They end up with drowning in the evacuation process. So many of the community right now are trying to communicate the message with the people that is just walking on foot is highly recommended. And the other effort that we attempted in the past few years is to create how can we communicate this hazard literacy education. And we took the model and put the model into a multi-touch exhibit, and actually housed at the Hatfield Marine Science Center, and using the Oregon, the South Beach State Park model as an example. Because many of you probably, how many of you visited Hatfield Marine Science Center before? I have, took my son there a couple of times, and so walking into that, you basically are signing some kind of agreement. Your voices and your conversation with other people will be recorded. So this is that when we integrate that model with the exhibit, it's hung up on the wall for 2 weeks, and it ended up with there are more than 500 people actually interacted with the exhibit, and that also. This is the 4 scenarios that we use. Basically the jetty route that I saw, I used earlier, which is here is the jetty routes. And there are different routes, other routes called rocks and sewer route, and the automobile evacuation from park. This basically people are walking to the parking place and then drive their car. So these are the 4 scenarios, and hopefully this video can. So this is one of the examples that a father and son was interacting with the exhibit.
Yeah, they're slow. Oh, that's the best route right there. All for me is the Rockway. So we know how to go now. We know we're here. We just go up to the rock. And those days are pretty far.
So in the conversation, we can extract basically some of the decision variables that they talk about, how they communicate, how they are interacting and drawing attentions. Other family members are joining the conversation, and this is one way to communicate. Increase people, increase the hazard literacy. So that's still that. Hung up was about 2 weeks, and we took it off. Right now, still more of an ongoing effort. So there's still a lot happening in that. And the other one, like I mentioned, is the vertical evacuation. So what are some of the best locations in the city that that we can place that vertical evacuation shelter? I mean, in Oregon, we don't really have a vertical tsunami evacuation structure. Washington now has one, which is the school. Some of you probably know. So if we put one of the vertical evacuation shelters in the middle of the beach area over here. So basically this is the beach area, and this is I believe this is Broadway. This is the one-way Broadway. Place that vertical evacuation shelter here, or place that in intentionally somewhere, which is probably we know that it's not going to be very helpful because the major of the people that we're simulating a scenario in a peak summer day that people are recreating on the beach, and you know, so this location does matters. You know, what we see from the simulation results is if we place that vertical evacuation shelter somewhere else, that mortality rate that you see from here is much higher than this location, which is more than 20%. This is in a single digit, about 6%. So this is the vertical evacuation shelter. The other area, another application is looking at the infrastructure. You know, like in an earlier scenario that we didn't consider the bridge damage, but we know that the transportation routes is going to be affected. Either bridge will be having partial or complete damage, or there will be landslides, or building collapse that are creating debris that will affecting the transportation network. So we look at this in unplanned transportation network disruptions, and basically looking at two scenarios. The base scenario and also on the right hand side is we call this U bridge, which is the bridges over here is taken out. So the idea is not every bridge is equally important, just like not every transportation link or segment is not equally important either. So what we see from this one is the base scenario, no failure is 6%. Is taking out the U bridge is increasing about 6.5-ish. So that increase of that is about 0.5%. And the other scenario is, okay, if we take out, what about take out a major bridge that are over here, which is actually the Broadway, connecting actually the major density of the population, going to the evacuation shelters. So, taking out that Broadway bridge is, increasing that mortality rate to 20%. So we're trying to, communicate the message that not everyone is equally important. I'm already over time. So I'll skip this one. It's basically evaluating what are the critical links in the transportation network. If Oregon, Department of Transportation will have billions of dollars to retrofit their bridges, and I mean, if we have unlimited resources, we can ideally retrofit everyone, but that's often the resources are limited. So the idea here is, okay, if on the horizontal axis is the number of the resource unit. One is one resource unit. It could be 1 billion, could be 1 million. So basically, there's different ways to spend that 1 million. 1 million is not going very far, but the different ways to spend that resource. For example, I retrofit this bridge to be pedestrian usable, or retrofit that bridge to be both pedestrian and vehicle usable. That probably took more resource to do that. So the message here is that the different ways to spend that resource will generate a dramatically different life safety outcome. So this could be, spending that money in a like not smart way and could waste that. But if we use that resource, with the informed decisions, and that could actually reduce that mortality rate significantly. I'm gonna be wrapping up over here. I was just, having a hard time. What are some of the conclusions that I wanted to, communicate today? I didn't put it as conclusions. I put it as major takeaways. I think there are a few messages, probably more than these, for the Cascadia subductions or earthquake and the tsunami. Like I said, it's not about if it will happen or not. And there are many people that are on this campus at OSU and many other universities on the coast are working on this problem. We know that it will happen. You're looking at the 10,000 a year geological record that happened. The average return interval is about 300 to 500 years. The last one was 1700 January of 26. So it's more than 300 years now. We know it will happen, but when it will happen and how do we prepare? I think there are a huge opportunity for the hazard literacy, with education, outreach to the community. At the end, it's about people and the community impact. And if we're, the research or if the work that we're doing is not helping or not affecting the people who are likely to be affected, that's not helping. So we really needs to do better in that hazard literacy education. And how do people recognize ground shaking as an earthquake, a natural cue for potential tsunami? And this happened in Palu as well. Many people have no clue that the earthquake, there will be tsunami following the earthquake. And even there are 2004 and 2011 events. And so playing, the other one is preparing for this requires multidisciplinary expertise. Engineers, social scientists, officials, emergency managers, community leaders, many people need to be working together this is a big effort. And the last one is we won't be able to prevent that, and we just have to be prepared and for that event. I'll stop here. I was already over time. Thank you for your attention. These are some of the publications that we generated in the past few years, and I'd like to acknowledge Brian Fuller was helping a lot in the park scenario, and Mark Farley and generating that exhibit at the Hatfield Marine Science Center, and Dr. Michael Lindell, and he is collaborating in many ways, and also Xuan from Tokyo, my collaborator, and these two professors actually helped a lot with the data collection in Palu, Indonesia. I'll stop here and acknowledge the support from National Science Foundation through the 3 awards from the CMMI division, and also Oregon Sea Grant to jumpstart the research a few years ago. Thank you again for your attention.
Thank you so much. So we have some time for a few questions. So if you're tuning in online, feel free to go ahead and put them into the questions pane. And we'll start with a question here in the classroom, and we'll just ask you to talk into the microphone so the folks online can hear.
Thank you for that presentation. It was very interesting, but also alarming. So now I'm going to have to practice running drills on the beach with my family so we can evacuate quickly.
Let me know. I want to collect your data.
So my question for you is the vertical evacuation. If Oregon were to construct one, how tall and then how many people would it hold?
That's a really good question. That's, how tall is it, which is the design of that vertical evacuation structure, and how many people, that's the shelter capacity. And right now, in the model, the City of Seaside model, that we didn't set the capacity of the shelters. We visited, some of them are high school and like hospitals, and each one has a capacity. But it's right now in the model, to be honest, right now we just take as people come, we'll take them. But we actually can set a counters in the model, count how many people actually used and went to this particular shelter, and how many people use this one, and also for the vertical evacuation structures. And the FEMA has a vertical evacuation structure, like report and study. And for the different type of structures, they could be, there are many of these on the coast of Japan. In Japan, there are designated vertical tsunami evacuation shelters. Height-wise, it's really depending on that scenario itself. We're expecting looking at a magnitude 9, which means that tsunami wave will be 10 meter or even higher. So which is 30 feet high of that wave. Not necessarily the wave will be interacting with the city at that height, but that's the scenario that we're expecting. So I'm not an expert in the structure design of the vertical evacuation, but there are many guidelines from Japan, from FEMA in this country, guiding that process. Chris?
Yeah, most people have a hard time sort of estimating how fast they can walk some distance, right? So part of when I talk with my relatives when we're somewhere and we're like, what's the evacuation route? They're like, well, I'm driving, and I'm like, well, you should walk because the roads are going to be all crowded, and you could walk there faster than. So have there any like time-based maps that sort of show like this is the time, this is how far you can get by walking, and then this is how far you'll get. Have they have communications like that in some of because your simulations are pretty convincing, right? About getting swamped by the wave.
Yeah, that's a good question, Chris. That the Ogami, in the past few years, they have been working. I believe there's somebody from Ogami from my communication. Oh yes. So they have produced pedestrian evacuation maps, and the other researcher, Nate Wood, some of you probably know his name. is with USGS. He has been working with, on the pedestrian evacuation for quite a while, and also using GIS to visualize, by 5 minutes, this is the parameter that you are likely to be hitting, and by 10 minutes, by 15 minutes. I think there are existing research on that, and also there are maps produced for some of the community. I wouldn't say all the communities. And one of my collaborators, Dr. Michael Lindell, and he got a project, from FEMA, and basically evaluating the evacuation products effectiveness, and including those evacuation maps. And also they do survey and try to understand people's map comprehension. That was actually happening in Portland. Using the scenario is a project also supported by National Science Foundation, looking at a volcano scenario like Mount St. Helens, knowing, basically point out, okay, name three places and gave me the general direction of that 3 places within the city or outside of the city. So I would say, to make it short, there are research on that, and there are plenty of empirical data available regarding pedestrian walking speeds, and many of our planners even, Dr. Kelly Clifton also, I know that through some of the video and through the counting of that video from the intersections and how people walk, cross the street intersections. But in the real disaster, empirical data that capturing that from real disaster, those data are generally lacking, because in those scenarios, our first response is not, okay, let's collect the data over there. It's it's the response, and I feel that in general in this area, empirical data is very, very valuable. That's why the Japanese data, from that event in 2011, it's a really neat and empirical data. That's really the real people's behavior, their speed, and given us from the cell phone or GPS. Yes.
I wanted to ask, how does the presence of earthquake affect your model, and how is the network hampered because of it?
That's a good question. In this scenario, in the scenario that you look at over here, we're looking at magnitude 9.0-ish. And there are many different other, like for example, magnitude 8.7 or 9.3. For each of those different earthquake scenarios, we have like the tsunami inundation files for each and every scenario of those. One of the difference is that's actually the work that my colleague, Dr. Dan Cox, has been working on. And for those, basically the tsunami wave run-up height will be different for each scenario. And in terms of, the ground shaking that will damage the transportation infrastructure, like for structural engineers, people working on bridges, they use, the fragility curve to look at, on the horizontal axis is the PGA, on the vertical axis, the probability of that bridge is likely to be damaged. Different states to be damaged moderately, severely, and completely or minor, to just look at that. That's also reflecting the earthquake, earthquake damage from that. And there are also, the landslide maps for Portland, actually for the state as well. Togami is working on that, Oregon OSU is working on generating those as well. So it's a multi-hazard scenario. And really we have to consider, for a Portland scenario, it's probably not affected by tsunami, but it can be earthquake damaging those bridges on the Willamette River, and also massive landslides are generating in different parts of the city. And over that, the panel ERI just on April 1st on campus, you were there as well, yeah. So it's really we have to just integrate a different type of hazards to look at it. I had a conversation with City of Portland, that emergency manager, Carl Millar, I forgot her exactly last name, but they were, also doing bicycle, like using cargo bicycle and doing those type of drills, and how a cargo bicycle, when the cars are not usable, how can we use those alternative transportation modes? It's, probably cars are hard to navigate, but those lightweight transportation tools may play a role. And don't underestimate the power of a cargo bicycle. And when I read that article, oh, this can carry a lot of stuff. So I think those are some of the things that we should also evaluate, look into, and what are some of the alternatives. But back to your, the different magnitudes can be incorporated over here in the model. Yes.
This might be a really silly question.
No silly question.
But with increasing dependence on cell phones to navigate, and I don't, I haven't been in a natural disaster, so maybe you don't look at a phone. You're just like looking for the where you can run, and that's why signage is so important. But is there any kind of integration of emergency kind of pushes of communication to phone that it just pushes this is the fastest route out, walk, go from here to here? I don't know if it's is that a crazy question?
No, it's actually very relevant. As far as I know, there are, we cannot expect the cell phone will be functioning in the magnitude 9, and basically not just transportation infrastructure, communication, those cell phone towers and power lines, likely to be out of service for extended amount of time. Very likely the communication way is just a knock on the door and mouse to mouse. Scenarios that in the Mexico earthquake in 2017, when I visited and talked to the people, the professor who were hosting us, and he said the younger generation basically taking over the city. And the cell phone service was out, but not everyone. The WhatsApp was usable. So the WhatsApp become a critical lifeline, and also bicycle become a critical lifeline within the city. And so that's also motivating us. We're actually designing a survey to look at the use of bicycle in that, not for traveling long distance, but in that post-disaster recovery piece, there are many reports actually about the use of bicycle in the Mexico earthquake. So back to your question, I know that the California, they are building a sort of a warning system, just push that through smartphone, through iPhone. Professor Alex Bain in electrical engineering at Berkeley, he was either leading or part of that effort. I'm not sure what exactly they are at in terms of that system. But I know that, in the Pacific Northwest, UFO, Washington, and also working on some of the early warning systems as well. And I think my understanding is just we cannot just expect or, relying on the technology, because that's likely, even in normal days that could fail. And in that scenario is very likely not usable. So we have to be prepared. Without that, how should we navigate, and how should we communicate?
It sounds like bike companies should start marketing a new message of this is your, in the case of a disaster vehicle.
That's a good question. I forgot the gentleman's name, but he is living around Portland area. He maintained a blog. Was talking about disaster relief and how the inclusion of bicycle in a disaster toolkit can increase the household's preparedness. That was actually one of the questions in my one of the proposals that we submit is I feel that this area is requires more attention from my standpoint. I feel there's a lot of especially for the earthquake, those rapid onset disaster. For hurricanes, you have to travel from Florida to Georgia, probably not. But for these type of events, the tsunami is only inundating about a mile or two, and 2011, the most furthest part in inland is about 16 miles. It's really depending on the geographics. But I hope that I have partially addressed your question. There are only city answers, no city questions.
Thank you. So we have a question from online.
Yes.
Talia asks, what can we do to increase survival rates for people with mobility or sensory disabilities during a Cascadia subduction zone event?
That's a really good question related, with how should we care about the people are vulnerable, the vulnerable population. On our coast, many of you know that there are many people retire on the coast, not just from Oregon and from other parts of the country. One of the co-PI, Dr. Laurie Kramer, she has been working with some of the senior centers, having workshops, just meeting with and she shared with a story in our meeting is, one of the senior gentlemen, and he said he will never leave his wife, which is actually, not able to walk anymore, and leave her behind and leave, by himself. He's 90 years. I said, hey, I'm 90-year-old. I have a happy life. If this is the end of my life, I'll take it. And there are people that it's a different ways of reasoning. But what we are trying to do is actually trying to communicate with these group of people that if you actually leave early, if you actually increase your preparedness, knowing where to go and knowing the ways to go, but just leave early, that you are likely to survive in that situation instead of just not taking protective actions. So I think the vulnerable population, people with disabilities, is in the people that we should really give attention and providing alternatives. That what are some of the options that they can take? So that's so far that I can offer.
Thank you. Yes.
Yeah, no problem.
So we're coming up close to time, so we have time for one more question.
Hi. First of all, I just want to say the model and the visualization.
Yes.
I found that extremely powerful. In fact,
Thank you.
I'm pretty sure I heard an audible gasp the first time the tsunami came in Seaside. Yeah, it was you. Yeah. So one thing I'm wondering, it kind of strikes me that given network constraints, the mortality is probably highly correlated with how many people you're trying to get out of the inundation zone. It's probably not linear.
No.
So what I'm wondering is, like, for example, the Seaside, 2 o'clock on a Saturday in August is probably not the same as 2 o'clock on a Tuesday in February. Have you looked at, or have you looked at applications for, looking at land use and zoning, things like that? Because it just seems like this could be really informative to, how cities think about school siting, employment, housing density, things like that.
That's a really good question. Like I said, this model, as you see, we only consider that transportation network. I have a colleague at OSU, and Dr. Dan Cox and Dr. Andre Barbosa and a few of the structural engineers, they are looking at each and every building in city of Seaside. We keep using city of Seaside because it's there's one of the go-to places for tsunami. And I get a comments from a recent project that, oh, let's just try some other communities. There's many more coastal communities in Oregon that we should pay attention to. So ideally, long-term goal is we wanted to integrate that, not just the transportation network, but also the building, even the building type, like basically those wood structured or unreinforced masonry building and the different type, and also for the what type, if it's a business, commercial, what type of business. And those are the questions. There are people who work on that. I'm on this campus, Dr. Yu Xiao, and she has been, working on the recovery, business recovery. I have a lot of conversations with her. I hosted her actually at OSU as well. So there are, I would say, groups who are looking into business recovery and those building structure and building. And even, we actually need to consider the time that the people take to leave the building, not just from that, particular location, like a terminal time per se. And how we can do that. And I mean, ideally, what we really want to get is some empirical data, not just arbitrarily add, okay, let's just add some time in that simulation. Is how long it really takes for a household or people to be ready for that in that scenario. And I was thinking, can we do some kind of this type of just get some of the household who volunteer to participate and just get some empirical data. I haven't seen any empirical data in that sense. But over the past many events at Christchurch, American Samoa, and Tohoku, and there are many surveys has been done post a survey asking people after half a year, but there's a lot of information could be lost as well. But ideally, to keep it short, long-term goal is we want to integrate that. We have been having conversations, and many conversations are going on, integrating that structure, integrating the transportation, integrating those building information. And land use part, and I have a colleague at OSU in resource economics, Stephen Dundas, and he has been working on more of the social economic side. For example, if we use the money to create like a raised, like just a vertical evacuation structure, basically putting that a high ground over there, the cost of doing that versus doing some other protective actions, and that actually associated with some of the land use properties, land use considerations. In our model, we did not actually consider that in a greater way that we should.
Great, thank you. Before we end, we wanted to share that Portland State's Initiative for Community and Disaster Resilience is hosting Dr. Rob Olshansky. His book, After Great Disasters, yes. He's presenting here, and it goes through processes and outcomes of community recovery and reconstruction following major disasters from 6 different parts of the world. So if you're interested in that, that is happening on Tuesday, April 30th from 3 to 4:30 p.m. Thank you so much for joining the Friday Transportation Seminar, and a big thank you to our presenter, Professor Wang.
Thank you. Yeah. Thanks to everyone.
Please do come up and say hello. Thank you so much.
Thank
That
you.
was really, really
I know
wonderful.
the Dr. Robert Lansky, I forgot how to pronounce his last name.
Yeah, I'm not sure.
He actually he's leading a group to going to Palu in May.
Oh, okay.
Yeah.
Where you just were, right?
Yeah. He's part of the ERI.
Is he studying there as well?
No, he's a professor from UIUC, retired professor working in disasters.
Seeing you again. We'll
Yes.
see you around sometime.
We'll be in touch. Yeah. Thank you.
I can take that from you, and yes, thank you very much.
No problem.
Yeah.
The only part that I'm not worrying about is the parking.
The car, yes.
Yeah.
Let's attend to that.
Yeah, that's fine.
Is it in a garage?
In a garage.
It is in a garage. Okay, so I think we'll be.
Unless they give me a ticket, something like that.
We'll sort it out. We'll take care of it, I'm sure. Do you happen to know I think what they do is they give you a permit. And so what we can do before dinner or before lunch, we'll just walk right across the street to the parking place and get a permit. Yeah. And then we can slip it into your car. So yeah, let's do that in a few minutes. Feel free to grab some donuts if you want. And we are going to go to lunch. So.
Thank you.